Okay, we're going to continue with our writing functions as power series. So question number 20 is x cubed over x minus 1 squared. I'm going to use the second power series representation here. So I'm going to get my eye pencil out. Okay, there it is. So we're going to use this power series representation. N plus 1, x to the n. So what we know, so we have 1 to infinity, n plus 1, x to the n, for the absolute value of x being less than 1. Let's double check. 1 over 1 minus x squared is what you see here. Okay, that's 1 minus x squared. However, that's not what you see here. You got x minus 1 squared. So we're going to have to fix that denominator now using a little algebra. This is what I mean. I can factor out a negative 1 so that denominator could be written this way. And that's really negative 1 times 1 minus x squared. So using some algebra, we get negative 1 squared, 1 minus x to the second power, or that simply equals 1 minus x squared here. So this denominator of x minus 1 squared is actually the same as 1 minus x squared. Oops. I apologize. The square is outside. Alrighty. So they're equivalent. So we're going to look at the power series expansion now of x cubed over x minus 1 squared, which is x cubed times 1 over one minus x squared over here. We just showed those were equivalent because we have a power series expansion here. And this is the power series expansion. Okay. X cubed times the sum 1 to infinity, n plus 1, x to the n, for the absolute value of x being less than 1. Now, this term x cubed, by the distributive property, goes inside the summation. And by properties of beginning algebra, again, we're going to get n plus 1, x to the n plus 3. All right, let me write this whole thing down. This function is represented by this power series. And the absolute value of x minus 1 now over here is really, again, for negative 1 less than x less than 1. And it's an absolute value inequality. power series expansion. Oops. And I am really doing some typos here, so I apologize on this. That's the x squared is on the outside there. Let's double check. Yes. All right. So these are the functions as power series. These are some of the functions we recently defined for you. We can use those. Okay, now we got a similar question. Very similar. We're going to make use again of this particular power series. Let me write it down. That 1 over 1 minus x to the second power is described by m plus 1 x to the n, where we have the absolute value of x being less than 1 again. Okay. Let's double check. Okay. Now, I'm going to say focus on this x. We're going to replace this x with 3x. In all of these locations, we're going to replace that with the 3x. So, this is what it'll look like. Right? This is going to be replaced here. This is the focus. Replace that with the 3x. With the 3x. With a 3x there. So, this power series expansion will be 1 minus 3x to the second power. Comes 1 to infinity. M plus 1, 3x to the n. And that's good for the absolute value of 3x being less than 1 now. Now, you're just going to use a little algebra for this term here. Meaning we have 3 to the n, x to the n, so that the power series of 1 over 1 minus 3x to the second power becomes the sum from 1 to infinity, m plus 1, 3 to the n, x to the n. Now, that's only part of the answer because don't forget, we have this x squared term, really. So, x squared over 1 plus 3 to the x squared becomes x squared times 1 over 1 minus 3 to the x squared. We need the power series expansion for this. And we already found it. Yes, it's going to be good only for this interval, and we'll see what that interval is. But doing some algebra. Remember, this term that's on the outside of your summation by the distributive property now goes on the inside. So you now have x squared, n plus 1, 3 to the n xn. And the final answer will be x squared 1 minus 3x squared will be summation 1 to infinity n plus 1, 3 to the n, x to the n plus 2. This is going to be good for the absolute value of 3x being less than 1. So, there's really a couple of ways I can describe this interval of convergence. I can write this as, let's get red, -1 less than 3x less than +1. Divide the middle, the right, and the left by 3. So it's really only good for values of x between -1/3 and +1/3. This is our interval of convergence for this particular power series. All right. Inverse tangent. So for inverse tangent now, we need the power series representation for inverse tangent. We deduced this earlier today, and the power series representation is listed here. -1 to the n, x to the 2n plus 1 over 2n plus 1. Those are like how we describe odd powers, by the way. And it's again for the absolute value of x being less than 1. So it's an alternating series. Okay. So what we're going to do now is replace your x with x over 2. X over 2 here, x over 2, x over 2 over here. So that the inverse tangent of x over 2 becomes the sum 0 to infinity, -1 to the n, x over 2, that's raised to the 2n plus 1 power over 2n plus 1. So we're going to have to do some algebra over here. All right. Now, by algebra, properties of exponents, a over b to the nth power is an over bn. So this power series, -1 to the n, is x to the 2n plus 1 divided by 2 to the 2n plus 1, and that's simply over the factor 2n plus 1. So we have a complex fraction. More algebra to do. Okay. Let's see what we have. I'm going to put the 2n plus 1 here, and put 2 to the 2n plus 1 over here. And that's the final answer. So this is inverse tangent of x over 2. The sum from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1, 2 to the 2n plus 1. Now, this is good for the absolute value of x over 2 being less than 1 over here. This is our interval of convergence here. So we can apply that again by saying -1 is less than x over 2, which is less than +1. This time, we multiply the left by 2, the middle by 2, and the right by 2, getting -2 less than x less than +2. Here's our interval of convergence. And now we have an additional power series expansion here. All right, I think that's pretty much it here. We can continue with a lot of permutations of these kind of problems, but I'll stop right here and send it to you guys. And I hope you guys appreciate what we have done.